Hello, am I audible?
Yes, sir, you're audible.
Okay. Good afternoon, sir. T03. Thank you, sir.
Please share your screen, sir.
उदय जी का उनका माइक बंद है.
सर उदय जी वाला भेजिए वाला वो बायोग्राफी जो कहाँ भेजे आप भेजे थे
नेट चला गया क्या?
Respondents should seek points and point achievement for each question. Respondents correct answer after grade are released. Respondent.
Sir, can you hear us? Sir, your mic is not enabled.
Not enabled.
Please unmute your mic, sir. Hello. Hello. Yes, sir. Your mic is yes, sir. Your mic is, I think. But we have made you presenter, sir. I think. Okay, okay. Let me see. No, sir. We have already make you presenter. You can from your side only. You can unmute. Yes, sir. Earlier it was muted. Yes, sir. Yes, sir. Again muted, sir. For a second, you have unmuted yourself. Again muted. Yes, now it is unmuted, sir.
Here I am getting only select participant can
No,
unmute.
sir, your voice is coming now. Your voice is coming. You are audible, sir, now?
I am getting
Okay.
the trademark.
Okay. Sir, let me first introduce to you. Just wait a minute, sir. Let me introduce you before that ending.
Okay. Sir, my slide is visible, sir?
Yes, sir. Your slide is visible.
Okay, sir. Please continue.
Okay. So all the attendees, now the lecture is from Dr. Uday P. Kambade, sir. He is basically semiconductor laboratory scientist working in from 2001. He is now head of the division in digital design division and VLSI design group. He completed his BE from Walchand Institute of Technology in 1989, done PG diploma in VLSI design in 2001 from University of Pune. He has several work experience involved where he involved in the design and development of digital application, specific integrated circuits. Worked on 16-bit and 32-bit, 64-bit microprocessors in Shakti processor, realization at SCL, developed digital ASICs for camera electronic timing sequences for CCD devices, ASICs for Chandrayaan-2, Chandrayaan-3, Aditya L1 mission, 9 digital ASICs for Indian Railway were developed, created in-house standard cell library characterization of EDA tool, created in-house SPRAM memory compiler, providing design PDK EDA support for ISRO, DRDO, DAE, SMDP Institute under MITI, presently coordinating different RTL to GDS2 ASIC projects, multi-chip module processor and PDK development activities also he is doing and involved in. Now he has several publications like high speed dual rand doming logic for SCL 180 nanometer semiconductor technology, fast transistor adiabatic logic with NMOS pull down configuration in standby mode, which has published in International Conference on Computing Communication and Control Automation. Development next publication development of IB's model for SCL 180 nanometer technology under 3.3 volt supply. Design methodology for asynchronous NCL circuits in Synopsys EDA tools. SNUC Israel submitted. Power analysis, attack resistance configurable ASIC implementation under Indian Society of System for Science and Engineering, Ahmedabad chapter. Next, design of FPGA building blocks using LT Spice, which was published in 4th International Conference on Recent Development in Control, Automation and Amplifier. His area of interest includes digital ASIC design, low power design, design for reliability, manufacturability, PDK development. He is also involved in PDK development and standard cell library development. So this is the brief intro of Dr. Uday P. Kambade, sir. He has several experience in SCL and all the other industries also, and he is working very influentially towards the fabrication theme of India. So now you can continue, sir. Please continue, sir, with your lecture. Hello, Uday sir. Are you? Am I audible to you, Uday sir?
Faculty. Audible, sir?
Yes, you are audible, sir.
Okay. So first I will thank IIT for giving the opportunity to interact with all the faculty and all the attending this Jan workshop. So mostly you are working on the most neuromorphic computing and the state of the art high high performance. That is now we are working in this semiconductor era, and now recently, few years back, the government of India has that means enabled semiconductor policy. So with the aid of the semiconductor policy, many PLI, DLS scheme and this this we are working on this so Am I audible?
Yes, sir, you're audible. Let me make you presenter first.
Okay, sir.
Incoming voice call from S.
Hello. Yes. हाँ बट सर मैंने आपको प्रेजेंटर बना दिया सर, आपकी तरफ से अनम्यूट कर सकते हैं। हाँ ठीक ठीक। It is coming, I think. No, sir, no. Yes, coming. Yes, your screen is visible now. Screen. No, not audible, sir. You are muted from your side. I made you presenter, sir. Okay, let me change the setting for all. Then the last option. Okay, sir. Now you are unmuted. Now you are unmuted. Yes.
Yes, sir.
Actually,
I will share.
yes, sir. You can share your screen. Your screen is visible. Just make it in full form. View slide view. एक message डाले requesting other to
Am I
mute
audible?
themselves. Yes, sir. You are audible.
Okay, sir. We can start, sir, then.
Yes. You can start, sir.
Okay. So here to use this knowledge of your
Sir.
design. Hello.
Yes, sir.
Please make the slide.
Am I audible, sir?
Yes, you are audible, but I think network due to network fluctuation, your sound is breaking, and also the slide is not slide view not is there. Your screen is visible. That means your PPT is visible, sir. But make it in enlarge, make it in slide view, so that it will cover the whole screen.
Is it okay?
Okay, you.
Okay, you can continue, sir. Go ahead, sir.
Lot of IPs and we require a lot of systems. So discuss about what are the issues we face at the time of design and what care we should take at each of the design. We'll discuss about SoC and what we can for while making the system of chip. is the brief outline of my talk. We will discuss what are the SoC, why it is required, and for that implementation, what are the inputs are required at how to do this reliability analysis at each stage, during placement, during routing, during chip finishing, during physical verification, and during its timing analysis. So we will discuss about the what are the what are inputs and what constraints should be given so that processing system contained in a single package. So there are multiple systems. So suppose we are having one processor, we have multiple data acquisition, making one system which can take care for the protection. Just we have seen them just we have seen the um,
Excuse me, sir. Sir, I'm interrupting. Uday sir. Uday sir. Uday sir.
So
Uday sir.
a lot of mangoes in our fruit. So what the hello, am I audible? Hello.
Yes, sir. Yes, sir. You are audible.
Okay, I will share this. Yes. And slide is visible.
Not yet, sir.
Okay, just I will share.
प्रेजेंटर बना दिया प्रेजेंटर बना दिया ना
Hello.
Yes,
Slide
sir.
visible?
Yes, sir. Your slide is coming now.
Yes, introduction. Okay.
Yes, introduction. This slide.
Okay.
Yeah,
As I
once change the slide, whether it is changing here or not, we can see.
okay. SoC. SoC.
No, sir, not changing. It's still on the introduction.
Description.
Yes, it's still introduction, sir.
Some network issue may be there.
Yes, yes. Actually, Microsoft team needs very good internet connectivity. Otherwise, it will not perform.
Net is okay because normally we are using same internet for other meeting also.
Now changing. Yes, now changing, sir. Now it's showing typical SoCs.
Okay. Is it changing?
No, sir. It is stuck on its typical SoC page.
Okay. I will do from other device. I will check. Just
Okay, sir. Okay, sir.
1 2 minutes.
Okay, sir. No issues.
Okay.
Take your time. Sir.
Hello.
Yes, sir.
Slide visual.
No, not slide visual, but your voice is clear now.
Okay, just I will share. Hello, is slide visible?
Yes, sir. Now it is coming on full screen, sir.
Okay, sir.
Just change
This one?
not
Contents.
it is on the first slide only. Now it is changing, sir.
Oh. Now introduction.
No, it's yes, introduction is coming. Yes, sir.
Okay.
Little but delay, but it is coming, changing now.
Oh, okay, sir. We will then start, sir. Okay.
Yes, sir. Please start, sir.
Yes. So, are you are already aware of the some application? You can start with the development of the particular system. For the system, you should know what are the it's my ecosystem and what is my environment. So, according to your environment, you can start the SoC design. And for SoC design, you require some processor, you require some memory, input/output ports, some peripheral devices, and storage. So, according to application, you can first segregate the blocks and start integration of the particular heterogeneous devices. So you may require some processor core, single core, multi-core according to your application. So before starting your any design, you should aware of what is your exact requirement. Do you require single core? You require RISC processor or sys processor, or you require only some digital controller and some memory devices. Suppose you want to make some say, simple farmhouse SoC. You want to protect your product, maybe mango, coconut, or any farm. You can deploy one simple IoT controller. You can have some LoRa block, some data equation for the detection of your particular event. So if there is any event, you can note down the event, and the processor will calculate the what is your initial inventory or what is the initial stock, and then it can use the LoRa or any your uh, any transmission. It can you can get all the information at your farmhouse, and you can process and protect your product. So typical SoC may contain single core, multi-core. You can have multi-core or heterogeneous processor. Sometimes there are we are using crypto processor so that you can synchronize, or you can have multiple this architecture in multiple environment system. So typical SoC may contain different digital block, analog block. You have to integrate that in a single system. So for that making single system, you may require your expertise at front end. You may require expertise in back end. So we'll discuss how to integrate all the blocks, how to integrate all this different domain topology in a single system. And for that single system, we should have command on our design from architecture level, from front end level, back end level. So we'll discuss what are the issues we face at the front end, what issues are at back end. So uh, uh, most of you are working on this high performance computing or neuromorphic computing. So whenever you are starting your design, or when you are starting your any system design, you should aware of what is its environment. So when you are doing any logic design, you should aware of what kind of architecture is required my particular ecosystem. So once logic and front end design is over, then we can convert to particular technology. Suppose you want to perform one computing at 1 gigahertz. So at present we have SL 180 nanometer. Suppose we want to perform 1 gigahertz core or 2.4 gigahertz core. So you have to do feasibility whether what kind of logic design and what kind of this PDK or process is required for your particular design. So you should aware of the what is my requirement, what is my goal. So before starting my logic design, what kind of architecture I should select, and what kind of process technology is required for implementing 1 gigahertz processor. Or I just want some IoT system at 100 megahertz. So 180 nanometer is also sufficient. So before starting logic design, you should aware of what are the ecosystem and what are the resources available with respect to fabrication, with respect to testing, with respect to my database. I should aware of the my complete ASIC requirement. So once requirement is there, you can start logic design. In front-end design, you can do synthesis and you can do DFT. At the time of backend, you do floor planning. So we'll discuss all these steps in next slides. So when you started your architecture and your functional simulation is over. So when you are doing RTL design, you should aware of what is my hardware goal, what kind of synthesis netlist I will do. I should have thorough command over my RTL. The RTL should be verified. I should have the complete functionality clear to you. So when you are doing the RTL, so you should aware of what kind of hardware it is going to implement. So just please let me know audiences from which background they are doing MTech, PhD or undergraduate, or they are doing some research.
So they are basically from most of them faculty, research scholars, and MTech.
Oh, okay, sir.
Okay.
So most of you are aware of the what are the what precautions you should take care at the time of your front-end design, RTL design. So can anyone can tell what are the RTL design? What is the difference between RTL design and this behavioral design? So we are talking from RTL to GDS2. So before starting your design, you should aware of you are a hardware engineer. You are not any software engineer. You are writing the code for a particular SoC. You are selecting particular core. So while selecting this hardware or writing this code, you should aware of the when you are doing synthesis, you should aware of what is the content of your RTL. So what care should I take on at the time of RTL? What kind of analysis I should do at the time of RTL design? You should aware of. So otherwise, what will happen? Your system is working at the RTL level, but after synthesis or after layout or post silicon, you will get some surprise. So what is RTL? Can anybody tell? What is the difference between RTL and this behavioral model? So in front end, first we will do behavioral model, and then we go for RTL, and then we go for synthesis. What is the meaning of RTL?
RTL is basically the register transfer label Verilog code or any hardware language in which we are going to write the code for the hardware thing.
Okay, so when you are writing any code, register transfer level, like we were writing code for counter, we can write that counter wait for 15 clocks. Otherwise, we can write the code for the counter in terms of it's a counter code in VHDL. So when you are writing code, the code should be synthesized. So
Yes.
whatever you are writing the code, when you are writing the if statement, you should aware of what is the inference of if. If you are writing if, then there is a formation of latch. If you are writing if else, there is formation. It will infer the flip flop. So you are the hardware engineer. You should aware of the what kind of RTL code you are writing, what kind of coverage analysis you are doing. So if you are writing the RTL code, you should have thorough coverage analysis at the front end level, so that you can have proper branch coverage, you can proper FSM coverage, toggle coverage, so that your code will be working, and there will not be any surprises at the silicon level. Suppose you are writing code and you have written quest statement. So and if you have not written the default statements, so what will happen? It will work on the what are the case you have defined, written in the code or you have verified. That will work fine as per your intention. But other cases which are not intended, that may malfunction or that may create some surprise at your post silicon level if you have not defined that particular default cases. So while writing the for any SoC design, if you have IP, if you have soft IP or hard IP, so that what are the RTL in soft format or in netlist format, you should aware of the what is the quality of the that IP. So you should have that coverage analysis. You should have the verification benchmarking with which the IP was available to for the integration in the SoC. So once the frozen RTL is there with all the coverage analysis, you should start the synthesis, and after synthesis, you should start for the this actual integration at the SoC level. So yeah, if your RTL is working, your gate level is working, then you should proceed for the further layout stage. So this is the typical flow which we are using for SoC design, and we'll discuss what are the challenges we'll face at each stage of the design. So RTL design is over. First we will do behavioral design, and then we'll go for RTL design. So then we go for the synthesis with the scan flip-flop. Our goal is the synthesis is to convert our RTL to technology specific gates, and we will make the netlist at the gate level. So, and we are using the DFT technology, scan flip-flop. Actually, we want our goal is to test our chip. So we cannot do everything through dynamic simulation. For that, we have to do scan-based flip-flop design for testing, so that we can have all the our input should be controllable and all output should be observable. So we have to insert the scan flip-flop so that we can have the proper ATPG patterns, and we can have better testing. So once your RTL is freeze, then synthesis is freeze, then we go for floor planning, placement, clock to synthesis, routing, and chip finishing. We'll discuss this in next slides. The details, what are the requirement of this. So for any SoC, we require gate level netlist, soft IP or hard IP. We require technology file from foundry. We require the timing constraint for the my SoC or chip. So whenever tracking, my clock frequency is 1 gigahertz, my clock frequency is 100 megahertz. So what is the meaning of that 1 gigahertz? What is the meaning of 100 megahertz? So when you are making clock for any system, we are specifying clock period as 100 or clock period as 1 nanosecond, 1 gigahertz. So what is the meaning of that clock, or my processor is working as 100 megahertz, or it is working at 1 gigahertz. So what is the meaning of that that period? So when you are starting our design, we have to constrain our design, and we are giving constraint as 100 megahertz. So what is that 100 megahertz? What is the meaning of that 100 megahertz? Which path will complete in 100 megahertz, that 10 nanosecond? Can anybody tell? If we are making any system, we have to give assign goal of 100 megahertz. So what is the, which duration is that 100 megahertz? Am I audible?
Yes, sir, you are audible. From
so
the attendee side, if anyone having the answer of the professor, he can give the answer.
So what is the meaning of 100 megahertz? Which path is 100 megahertz? That 10 nanosecond path. So you are doing a lot of simulation while you are making design. So you should, for giving the constraint, you have input as RTL. You are getting synthesis netlist, and for synthesis netlist, what are the input? Inputs are cell library from foundry, and you also require timing constraint. So we are giving timing constraint as a, we are giving constraint clock as a 100 nanosecond. So what is the meaning of this 100 nanosecond? What is, which describe this time period? Am I audible?
Yes, sir. Yes, sir, you are
Okay.
audible.
So
Yes,
when you are talking, it's my process is working as 1 gigahertz. My system is working at 100 megahertz. So we have to make one system, and for making the system, we will tell some characteristics. This system will work at 1 gigahertz. It can drive 10 PF load. Its input delay, its input is clock is coming from some PLL or some function generator. It is driving some it is processor. It is interfacing with some memory. So it is interfacing with 16 memory cuts. It is interfacing with some F244 driver. So this kind of system characteristics is there. So whenever we're making any system, we should aware of what is the environment of my system. So for you have written that written the RTL code, it is working in simulation. But now I am making its complete system. For this making system, I want to describe the design intent. What is my clock period? what is my input clock cycle, what is skew, what is its input delay, where input is coming from some PLL, then there may be some PCB traces or something, or there may be some function generator, some wires are there. So wire traces are there. So I should aware of in what environment my system will work. So 100 megahertz means, so for any system, there are some input, there are some output, there is some combinational logic, there is some sequential logic. So there are, in any system, there are 4 kind of paths. Input to, my input is coming from some PLL, that clock will come from PLL, it is going to my register clock through some combinational logic. So there is a path from input to register. There is path from register to register. There is path from register to output, and there are some path from input to output. Some buffers are there maybe. So there are 4 in any system. There are 4 kind of timing paths, and each of these paths are should be completed in my timing goal. What is my timing goal in this case? In this case, my goal is clock period is 100 nanosecond. So you have to specify what is your clock and what is you require from input, or clock should go from my clock source to my register in 100 nanosecond. So this is my goal. My register to register, in register to register, there may be some logic depth of some 10. So that should be completed in register to register. That should be completed in 10 nanosecond. My register to output, it will complete with the 10 nanosecond. So all the paths are, there are 4 type of paths. All the 4 paths should be completed in this 100 nanosecond. I have to specify what is my input delay, what is my output delay. It is driving some memory cuts, or it is driving some driver. So input capacity of driver, I should set as a load. So when you are making any system, you should aware of what you are making, what your is environment. So how many of you have done the synthesis and layout?
Yes, sir, I did the synthesis and layout.
Okay, so for synthesis, you should aware of the what is environment. Otherwise, it will, if you don't know what, because timing constraints are one of the important critical parameter which dictate the functionality of your system. Otherwise, it will work in simulation. If you don't know its environment, it is driving 4 memory cuts. This memory cut is having input gate capacitance of suppose 2 femtofarad or 10 femtofarad. So at 2 picofarad or 2 picofarad or 10 picofarad. So if you don't know that exact load, so that that may create the problem at the silicon level. So synthesis is just you are converting your HDL to gate level netlist. But gate level netlist, conversion of gate level netlist, the timing constraints are very critical parts, and which can dictate the performance of your system. So you should aware of the what are the my clock is coming from what is source. It is coming from PLL. So what is the we have to provide the uncertainty. So what is the jitter of my PLL? What are the traces of my PCB from PLL to clock? So whether PLL is internal or PLL is outside. So you should aware of all the ecosystem of your environment. So what is the jitter? What is the skew? What are the uncertainty are there? What is the input delay, output delay? So if there are, it is coming from some different system which are having some sequential logic. So what are the setup and hold of that particular system? So you should aware of the timing constraint is one of the important step. And if it is a if you are giving some garbage value, we are getting some garbage output, garbage input, garbage output. So defining system is one of the important step, and for that you should aware of what are the different parameters required for your synthesis. So first step is your RTL. RTL, you have to convert that to synthesis with the help of gate level netlist, and you require the cell library of your foundry. So it will convert to the technology specific library. So first thing is RTL should be free. It should have coverage analysis. It should have its complete verification. That dashboard should be have complete verification. And with respect to branch coverage, toggle coverage, all should be RTL should be free. Then we have to do synthesis with the particular technology and the specific timing constraint, and we have to use the scan based DFT methodology for getting the proper testing and we can have proper yield. Then we require technology file which contain the process information. How many layers are there? 4 metal, 6 metal. How many vias are there, and what is the pitch of that particular technology? What are the this parasitic RC models available for this? Then what are the design rules, and what are the definitions of the all the current resistance and timing? So these are contained. This will be provided by your foundry. Cell library will be provided your foundry or IP vendor. You have to provide gate level netlist and the timing constraint. So timing constraint, one of the important thing in the starting of the synthesis. So foundry will provide the technology file which contain then how many layers, what is the stack information, how it is pitched, its minimum DRC rules are provided in the technology file. So all the physical names, physical characteristics, electrical characteristics of each layer and routing information is provided in the technology file. So design constraint we have to provide. So for that you should aware of the environment. You should check whether you have RISC processor or sys processor. So depending upon your ISA set, you have to provide the multi-cycle path or timing path according to your requirement. Then we have to provide the foundry will provide the TLU plus file, which is the RC extracted models for your particular technology. Then you have to provide the logic library of all the standard cells. We require its timing model, power model, and DRC details with particular PVT conditions. Then we have to provide the physical library of each standard cells or IP. We have to provide the phantom view of each cell so that it can be used in place and route. Then one of the important part of your SoC, there are multiple analog blocks, some digital blocks, some IPs are there, memory cards are there. So you should aware of the what is my requirement, what is my goal. My goal is to minimize the total chip area, make routing phase easy, and improve ASIC performance. So I have to do PP analysis before starting. Suppose I want this particular SoC, and after synthesis I have some my power figure. So from that power report I can calculate how many VDD and VSS power pads are required. How can I do the power grid generation? How can I do a macro placement and location of IO pad so that I can have proper interface to the system. So at the time of floor planning, suppose there are some analog blocks. So in there are some memories, some IPs are there, memory IPs or some analog IP are there. So there are at the time of floor planning we should aware of the content of IP. So if you are using some LDO and you are having some analog blocks, some digital blocks, so with there at the time floor planning you should aware of the content of each IP. Suppose there are some ADC which are having some power dissipation of suppose 200 milliwatt, and LDO there are certain feature like in LDO can there are some auto shutdown function in my IP. After some temperature or heat dissipation, that IP may switch off. Suppose LDO or some blocks are there. So I have to place my IP. I should aware of the characteristics of each block so that I can place. Floor plan is one of the important step at the time of layout. So you should aware of the what is the power dissipation of each block. What are the high speed signal, what are the low speed signal. So you should take care of the signal integrity or power integrity at the time of floor planning. So what are the inputs I am providing to floor plan? Design netlist. Then I have some area requirement or power budget is there, timing constraints are there, and IO placement and macro placement information. These are the inputs which I will at the time of the floor planning. And what are the output? After floor planning, I will place my blocks, my IO will place, my macros will place. I can design the power grid. So power grid generation is one of the important steps. So because we have limited VDD VSS pad and we should get uniform VDD VSS, for that we are doing the IR drop analysis. So we have to, this red one are the power steps which are used to cater the IR drop analysis or EM analysis. So we should aware the power, EM and IR drop before starting my floor planning. So these are the typical guidelines we should follow while fixing the location of the pin or pad. Consider the surrounding environment. We should aware. Suppose my process is interacting with memory. Memory is placed on the right side. So I have to place the all that address by data bus on particular right side at top side. So depending upon your interface, you have to place the do the floor planning. So you have to provide sufficient number of power and ground pad on each side of the chip for power distribution. So power distribution and airdrop is one of the important steps at the time of floor planning. Avoid placing pin in corner where routing is access is limited. So your critical pin, like say clock, reset, you should place at the center so that it can have minimum routing and you can have better access to this high fan out nets like clock or scan enable reset pin. Should not be placed at the corner. Use multiple pin layers for less congestion. Never place cells within the perimeter of hard macros. Otherwise, there may be congestion with respect to that particular hard macro pins. Avoid placing cell under power steps. Otherwise, there may be some parasitic extraction for that selected cells. So we have to provide multiple power rings or power steps according to your power requirement. So what are the challenges we are facing when we are doing this PDN network, power ground network? So for that we should aware of what are the power ground pins are required. We should aware of what is my power, what is current density, and how many layers are available in my particular process, 4 metal, 6 metal, with this thick metal or that last metal. How wide should we make to minimize the voltage drops and reliability problems? How do we maintain the VDD VSS within the noise budget? And how to verify overall power distribution system? So these are the important steps we should take care at the time of floor planning, because with the floor planning, this is the foundation of your chip, and later we can do placement and routing. So power mesh design is one of the important steps. So if you have power of suppose 200 milliwatt, after synthesis where core power is 200 milliwatt, and my one power pad can support 16 milliampere. So I require minimum 2 power pad for each side. So I require total 8 power pads, 2 power pad each side. So according to your this core power with respect to SSO, with respect to EST, with respect to DC current requirement, you have to place the number of power pads. You have to calculate the width of power pad according to current density provided by your foundry. So after floor planning with respect to IP or macro, and with respect to IO pad and power strip, your floor plan design is ready. So you have to do airdrop analysis. So there are different methods. So after RTL, you have done the basic dynamic simulation. So you have to provide that dynamic simulation VCD file, and you have to do one basic static airdrop analysis and dynamic airdrop analysis. So this is very useful at the time of floor planning. So airdrop is one of the important steps for the SoC design, because power budget you have to allocate, and according to you have to do floor planning and the power mesh design. So what are the effects of airdrop in design? So drop might have metastability. If it is airdrop, normally we are using suppose 180 nanometer 1.8 volt, we can have 100 millivolt airdrop we can allow. So otherwise what will happen at particular, if it is airdrop is more, we can have some flip-flop might have metastability issue. Airdrop on functional it is working, but at some temperature corner or at some particular environment it can have some metastability issue. Airdrop on clock network causes hold time violation. Airdrop on signal nets causes the setup time violation. So for reducing this airdrop, what we are doing, normally we are in more number of power stacks, spread the logic so that any hotspot are there, they can be spread. We can use low power cells. We can add proper VRs. We can use clock gating so that we have to reduce the power. We can have proper CTS structure, clock to synthesis, and we can have power ground metal fill, and we can stagger the switching activity. So there are multiple ways for reducing the power. There are multiple ways to reduce the airdrop. So you have to follow multiple strategy according to your design environment. So we are using prime rail for this airdrop analysis. So if you have a question in between, you can stop and ask me. So without airdrop, without poor floor planning, we can get the airdrop with red one is the with violated according to our goal, and with proper airdrop aware layout, we can get this one. So we can have better timing with this right one. So after RTL synthesis and then your floor planning, then next step is the placement. So placement is one of the important blocks because placement can decide the access to the routing purpose. So placement, our goal is to minimize the total area and interconnect cost and minimize the wire length and therefore the delay. So our goal is to performance and in smaller area. So placement is performed 2 stages: course placement and legalized method. So first we place the course, then check the airdrop, and then again we have to legalize the position, and then we can start the logical optimization. So with respect to logical optimization, we have to do the critical area analysis, and we have to do the critical timing analysis. So if critical part do not meet the timing constraint, then we have to do resizing, we have to do buffer insertion, we have to duplicate and make the different partitioning. So according to our timing goal or area goal, we have to change our logical optimization methods. So these are some example of good placement or bad placement. So if there are congestion, there are less chances of we can meet timing easily. Then it's easier for routing. So we can see how many number of tracks are available for each block and how many violations are in the right one. So where to do this congestion analysis after each placement iteration. Our goal is to have less interconnect, less delay, and less power dissipation. So for mid, we have to do this placement analysis. So after placement, we have our design is ready for placement. Place design is ready. So after placement, there are, as we discussed earlier, there are issue with respect to skew. So our goal is to minimize the skew, and for that purpose, we are using the clock tree synthesis, so that we can get the clock signal at the minimum with minimum delay. We can get that at the same zero skew, but that is not possible. So we can have minimum skew. So minimum insertion delay is required and minimum power dissipation required, because after clock changes there are addition of buffers, but we have to minimize the buffers and we have minimum skew. So before CTS, we should have placement completed, power coordinates routed, estimation congestion should be acceptable, estimated timing it should be positive slack, and estimated maximum transition capacitance. We don't have any violation with respect to maximum transition, maximum capacitance. So we are as we discussed earlier, we have to give timing constraint, and the constraint is with respect to latency, that with respect to network latency, or that that will be the source latency, network latency, or uncertainty. So we should aware of the what are the my chip size, what is the latency, source latency or network latency is there, if how many this logic depth of my design is. So accordingly, I have to use the constraint source latency or network latency. So my goal is to reduce the skew, and for this reduction skew, I have to add some balance buffers. So cell library will have balance buffer with the, and during the CTS we are inserting the balance buffer so that I can have meet the setup time violation as well as hold time violation. So I have to meet the my skew goal. So total skew should be as less as possible. I have fewer clock tree buffers so that I have lesser power and lesser routing resources. More number of buffers inserted, then I can have problem with respect to power. Clock tree synthesis should be constructed using a double width, double spacing, so that we can have less signal integrity issue. Otherwise, that can problem the, because it is clocks. It is at the highest speed. Clock speed is highest, so we can use the double spacing, so that we can have lesser this signal integrity issue, and we have lesser this interference. So this is a typical clock to synthesize design. So we can have clock is reaching all the points within limited skew. So we have to take care of the crosstalk while placement. So this effect have already existed, but we have to take care at the lower nodes. So we should have greater wire and via resistance, more metal layers are available, lower supply voltage are available, and low noise margin is there. So there are a lot of chances crosstalk. So we can decouple this crosstalk using the different methods. So we can add the more spacing for high speed and low speed nets. We can upgrade the drivers. We can have more spacing. We can have shielding with the VSS. We can have addition of buffer. We can avoid the long parallel lines, and we can shield the power grid. So what are the once design is placed, floor plan is done, placement is done, CTS is done, where to the routing. So routing required lot of resources, and that they were to analyze how many tracks are available for one node to another node. So for that we have to do congestion analysis, and after congestion analysis we have to see whether it is able to meet timing. If not, then we have to change its routing methodology. So for that high placement density, too much routing is required on small area. We can have less displacement, so that at the time of placement, if we have to go through this congestion map, and if it is if a less number of tracks, then we have to change the placements. So in routing, our goal is to route in minimum number of iteration, and we can have less interconnect length. So we should have use multiple metal layers for top metal, and top M-1 layers can be used for power routing, and other layers can be used for the signal routing. So after placement and CTS, we can do one global routing, which can connect all the power grids and check the its IOTOP analysis, and later it can do the detailed routing, which can check the this timing analysis for the signal nets. So first one is the power routing, and second one is the signal routing. So when your design is ready, where to do this dummy metal fill. So whenever this semiconductor manufacturing, we are working at multiple layers like M1, M2, M3, or 6 metal, 8 metal, 11 metals. So we should require the uniform metal density with respect to we are doing CMP process, chemical mechanical polishing. So we require uniform density of metal and active NGC, so that otherwise if there is low density of the polygon, we can have overreaching. If a high density, then there are some underreach. So we can what we can do, we can add some dummy metal so that we can uniform preparation. So this is without dummy, and this is with dummy, so that we can uniform placement. If you have any query, you can ask in between. Am I audible?
Yes, sir, you're audible.
Oh, okay,
Yes.
okay. So this is the complete chip, so which is ready for our post layout simulation. So we cannot do post layout simulation directly. Before that, we are doing the timing analysis. So what are the steps before going for the timing analysis? We should check the functionality, formal verification, ensure the functional equivalency of the logic level between two implemented, original versus the final, RTL versus synthesis, or we can do RTL versus synthesis, or synthesis versus post layout simulation. In formal verification, we are using formality for doing this netlist versus RTL netlist versus synthesis netlist, or synthesis netlist versus RTL. So formalities or conformer tool are used for the formal verification. So it will a formal verification tool just do the functionality. It will not do timing. So timing, we have to do static timing analysis. So we'll cover this next slide. So after your the placement and routing is done, we are checking the physical verification. So in physical verification, we are checking the DRC results. So what is the DRC results? So it can check the minimum metal width, minimum metal spacing, minimum density, ESD rules, or minimum channel length of transistor. So in DRC, we are checking whether design can be manufactured or not. So like here minimum DRC minimum width is minimum gate length is 0.18. So if I have 180 nanometer, our gate length is 0.18. If you are using 130 nanometer, its gate length is 130 nanometer. So what DRC rule will tell? It will tell the what is the minimum DRC, minimum width or minimum pattern can be allowed for if minimum width is 0.18 and if we print 0.13, so it will not be printed. If what is metal to metal spacing? Suppose metal to metal spacing is 0.23 micron. If we made 0.2 micron, so there may be if spacing violation is there, then that two nets will get shorted. So there are certain rules with respect to width which cannot be printed. If there are spacing rule is violated, then it can there are shorts. Sometimes it is open, sometimes it is short. So there are certain loop. Here we are seeing one transistor. Okay. So PMOS and NMOS we are seeing. So if that poly, there are certain rules like 0.35 micron extension, poly extension to active, it's 0.35 micron. So if this extension is 0, what will happen? There are certain rules, poly extension to active, 0.35 micron, like here we have seen. With minimum metal width, if it is violated, the nets cannot get printed. That nets will be open. If metal to metal spacing is violated, the metal gets shorted. Okay. So like there are certain enclosure rules there, like there are extension rule like this. Active, red one is active and green one is poly. Are you seeing this PMOS and NMOS? Hello.
Yes, sir.
So what will happen if this extension is not there? Poly extension is not there. Red that 0.35 micron. Will happen if that extension is not there? What will happen if it is instead of 0.535, if it is 0.3, if it is 0.2, if it is 0, what will happen?
It will show
Whether
the
we can
DRC,
manufacture or
DRC error.
DRC.
no, it will show DRC error. Like what we should, it will show DRC error. But as a hardware designer, you should know what is the consequences of the DRC error. Suppose like here example, minimum metal width is required 0.18. If I draw a polygon of 0.15, what will happen? It will not print, because minimum that pattern size required is minimum printable 0.18 is required. You have drawn 0.1, it cannot be get printed on nets less than DRC metal width can be, we can find them as open nets. Okay.
Yes.
So similarly metal to metal spacing, yeah, the spacing is suppose 0.23. Then if we made spacing 0.2, then what will happen? There are the two nets get shorted. Okay, the DRC error, but we should know what is the consequences of that DRC error. If we DRC error, then it will get shorted. Similarly, this extension, what will happen? We will get DRC error. If instead of 0.35, are you seeing this 0.35 poly extension? That red is poly and green one is active. So if red extension, the poly extension is less than 0.35, what will happen? Suppose it is 0, what will happen?
Printing will be not done.
Printing will not be done, or printing will be done.
Okay.
Because there is some that active this active is there and poly is also there. Extension is not there. But in case of metal width less than that thing, it will not print. But it is extension is 0.35. Are you seeing this extension 0.35 poly extension over active? Red extended above green area active. So how many of you know topology of NMOS and PMOS? So everyone is aware of NMOS and PMOS. Okay, we are learning for our first years electronics. So what will happen if we short the source and drain? What is the channel of the MOSFET? So
Source to drain.
That connection.
so suppose there is no poly extension then source and drain will get shorted.
Yes.
So what will happen? We are making PMOS or NMOS. So when source and drain, so one pin is get. Here we are shorting if there is no extension. What will happen? Their source and drain get may shorted. Okay.
Shorted. Yes.
And there is no formation of any channel, and we will form one pin is the get, another pin is source and drain connected. So it will form the MOS capacitor.
Yes.
So as a hardware engineer or electronic engineer, you should aware of what is the consequence, whatever you are making layout. It is giving DRC error, but you should aware what is the consequence of DRC error. Your intention is to draw the PMOS, and you are making the PMOS capacitor. You are making MOS cap. Understood?
Yes,
So
sir.
you should don't run DRC. You should aware of what are the consequences of DRC. If some mistake is there, what will happen? You want to my intention is to make transistor, but you are due to some your silly mistake or some typo or something command, you have made less extension, it will form the capacitor. So you should aware of what are the step you are doing at RTL level, at placement level, at DRC level, or if you are doing full custom layout, you should aware of what is the meaning of rule and what is the consequences of rule, physical consequences. So if it is violation of that DRC rule, you want transistor, but due to there is no channel, source and drain get shorted, and you will become capacitor. So DRC is the physical verification. Some rules are which we cannot manufacture. Some we can manufacture, but its topology will different. Sometimes there are ESC related rules. Suppose there are contact at far place, then it will form some latch up issue, or it can have some that if substrate contacts are far from your source or drain, then it can form that latch up issue due to that annual resistance or P-tap resistance will become more, and your SCR may get triggered. So there are some IO rules, and there are minimum channel length of transistor, which I told like 0.18 in this case. So you should aware of what are the design rules. Just don't run DRC, but you have to take care at each level. So at RTL level, you should aware of what is the consequences if there is branch coverage violation, if there is a FSM coverage violation. What if I am not returning my state to some ideal state? What will happen? It will work abruptly if you have not defined all the cases, all the branches of your system. If you have not written, if else, it will form latch. So you may face problem at the time of STA or latch. So you have to, whatever you are doing the hardware design or SoC design, you should aware of the each stage at each level. So because these are the fundamentals, like the what is the MOS, what is the capacitor, this should be ये पक्का होना चाहिए. So that's the, otherwise in simulation everything is working, but at the silicon there you will get some surprise, and these are very hard to debug this kind of silly mistakes. After that, you have to do layout versus schematic. What is your RTL versus schematic? In a layout versus schematic, you are finding the shorts open or some component mismatch, missing components, or some parameter mismatch. So layout versus schematic is one of the important steps. Sometimes there are some shorts are open, or sometimes some components are missing. So what is your layout versus what is your RTL? You can compare, or your layout versus schematic. Then there are certain layouts that can be manufactured, but you may face ERC, that we call ERC, electrical rule check, and that you can form some antenna. Like in this case, this P substrate, and then the poly is connected to metal, long metal connection is there. So at the time of this manufacturing process, to prevent the plasma electrostatic discharge damage, where to limit the length of the metal area restricted. So for that, otherwise what will happen at the time of manufacturing, the charge will be get accumulated on this particular metal, and that can be transferred to the poly, and poly can break down. So we have to reduce this 1000 micron length to some is less than some ratio defined by the foundry, and we have to add some jumpers at the particular length, or we have to add the diodes, so that if there is charge connected, then that can be, as shown in the right side, that can be grounded through that particular diode, or we add some vias or jumpers at a particular length, so that we don't have the antenna violation. This longer length metal connect can be manufactured, but it can cause electrical or reliability issue. So there are certain rules which cannot, with respect to DRC, that we cannot manufacture that particular polygons. We can, certain DRC rules can signify the topology, like transistor versus capacitor. Certain rule define the antenna. It can be manufactured, but they are causing reliability issue. There may be, if charge is more, then it can break down the poly after a particular ratio of the metal area to your maximum ratio of contact area to the GC area on active connected directly. So it should be greater than 10. If it is greater than 10, then it can give some antenna violation. In this case, metal area to poly area, it can give antenna violation. So for fixing antenna violation, we have to set up antenna rules, we have to calculate the violation and place antenna diodes or add metal jumpers, metal vias. After DRC, LVS, we have to do parasitic extraction. So we have to calculate the delay, a process of creating electrical representation of in terms of resistance and capacitor. We call that as a parasitic extraction. And this will be used for the delay calculation, STA, circuit simulation, and signal integrity analysis. So we have to calculate the lump C or lump distributed RC or distributed RC and coupling capacitance. We have to find all the parasitic extraction in different modes, and we have to do the timing analysis. So timing analysis is the one of the important step. We cannot do dynamic simulation or dynamic simulation of each particular all the input combinations. So for that, we are doing the timing analysis and STA. So we're once we'll do layout, and then again we'll do timing simulation and STA, static timing analysis. So what is static timing analysis? Someone has done synthesis, I think someone told. So what are the timing of any system? For any system, we are doing some dynamic simulation, but dynamic simulation for each node is not possible. So we are doing static time analysis. What I have told, like system is working at 100 megahertz, then it can do all the my timing path should pass within the 10 nanosecond, 100 megahertz. So what I can check, what should be completed in 10 nanosecond. So what are the characteristics of any inverter, or what are the characteristics of my flip-flop? So STA will do timing analysis, but what are the timing characteristics of my any system or any cell? What I can do in STA? What are the timing characteristics of any flip-flop? What are the timing characteristics of any buffer? What are the characteristics of any buffer? So tool will do the STA, but what action I should take? So what are the timing characteristics of any flip-flop, any sequential logic?
Power source we have to remove. Without power, we have to check the timing.
No, flip-flop के टाइमिंग कैरेक्टरिस्टिक्स क्या है? फ्लिप-फ्लॉप है आपके पास एक लैच है कोई, तो उसके टाइमिंग कैरेक्टरिस्टिक्स क्या है? हाउ कैन यू डिफाइन अ फ्लिप-फ्लॉप? व्हाट इसके फीचर क्या है? जैसे मैंने प्रोसेसर को बोला ये 1 गीगाहर्ट्ज पे काम करता है, इसका 16 मेमोरी उसमें 1 गीगाहर्ट्ज क्लॉक है, उसमें 16 एमबिट कैशे है, उसके अम्बा बस है, उसमें इट कैन सपोर्ट SPI और UART इथरनेट है. इस सिस्टम एक के कैरेक्टरिस्टिक्स है, ठीक है. सो वैसे फ्लिप फ्लॉप के व्हाट आर द टाइमिंग कैरेक्टरिस्टिक्स ऑफ एनी फ्लिप फ्लॉप? what are the timing characteristics? जैसे मैंने प्रोसेसर के कैरेक्टरिस्टिक्स बताए, वैसे इसके क्या फ्लिप फ्लॉप क्या हो सकते हैं? फ्लिप फ्लॉप का डेटा शीट आपने देखा होगा या बफर का डेटा शीट देखा होगा. So STA is the static timing analysis. We cannot do the dynamic simulation of each gate of circuit. So each cell, inverter, NAND gate, flip flop, latch will have its timing characteristics. For inverter, its timing characteristics is input to output delay TP, LH, TPHL, low to high, high to low. ठीक है. In case of flip flop, similarly, what are the for flip flop? It's clock to Q delay, setup timing, hold timing. So in STA we are checking. Suppose a shift register है आपके पास. So if you are making shift register and what are its characteristics? It can pass one flip flop to pass data from one flip flop to another flip flop. So एक दो flip flop है. So what timing path I will check? Input is coming and I am checking the clock to Q. How much time it will require from my data to Q, clock to Q timing. Then I will see the what is the setup time of the flip flop or the setup timing, and similarly for the next flip flop I am checking the hold timing, the clock period plus hold timing. So कितने टाइम तक मेरा डेटा होल्ड रहता है सेकंड फ्लिप फ्लॉप के, जो कैप्चर कर रहा है और जो लॉन्च कर रहा है उसके लिए सेटअप. So you should do the timing analysis, but for timing analysis you should know what are the fundamentals of the timing. What is setup time, what is hold time, what is recovery time, what is removal time. So suppose you get the setup violation, what you will do? Setup violation कैसे ठीक करते हैं? So for making setup violation, you should add some driver with bigger setup timing violate हो रहा है, means you have to add some buffers, or you have to add some bigger driver, or you have to change the interconnect length. In case of hold violation, you have to add some buffers in between that particular register to register path. So timing analysis तो हो गया, but setup violation आ गया. What you should do? You should setup time ठीक करने के लिए क्या करना है आपको पता होना चाहिए. Hold timing के लिए क्या करना है वो पता होना चाहिए. So SoC design में challenges तो आएंगे. What we do? Our fundamental should be clear. Like what are the DRC, what is the topology, what are the setup time, what is hold time. So in static timing analysis, suppose there are 10,000 gates and suppose there are 10,000 gates and 30,000 paths. So it will check the timing analysis of each node, whether it is meeting setup time, hold time, its delay, or suppose the buffer is driving 16 fan out. So whether it is meeting the what is the fan out of that or fan in of that particular 16 drivers. So it will check the its timing versus timing and the loading condition in timing analysis. So it will meet all my timing condition within particular given goal. So the goal of this SoC design is to make system, but for making system, our fundamentals should be clear, and we should learn not as a software engineer. We don't goal is not to write the code for counter or code for any your ALU and do simulation. Our goal is to write a code in sync what code you are writing. If you are writing if, what will its hardware? It will infer the latch. If you are writing only if else, it will become the flip flop. If you are writing the case statement, then you can form some decoder. If you are writing the this if else, then you can form the multiplexer. So you have to write the code in such a way that what is the hardware, and if you are getting some violation, how to do that analysis. So static timing analysis, for doing static timing analysis, you should have the fundamentals of basic, what are the buffers, what are the flip flops, what are the latches, and how to modify that timings. With the help of your basic fundamentals should be clear. Otherwise, tool will do everything. It will give that report. You have some setup violation, you have some hold violation. But what to do next? For that, you should have the basic info. Or if you are getting some recovery or removal violation, what you will do? So for STA timing analysis, that recovery, removal, or a setup or hold, all this timing should be pakka. So after our final goal is to test our circuit at the silicon level, and for the testing we have to add the automatic test pattern generator. So we are adding scan flip-flops, and we are using stack at 0, stack at 1 in methodology for checking all the my inputs and outputs and all the my gates. So this is the typical flow which are following, and at this stage we have to thoroughly analysis from SDL level to synthesis level to your layout, floor plan level, placement level, then physical implementation level, then STA level, and physical verification. You should have thorough knowledge of all the things, and you should aware of the what are the challenges like drop, like timing challenges, drop challenges, what kind of challenges we are facing. Suppose we are not able to meet the timing after this timing analysis, we can change the placement. If that is not there, then we can do the floor plan again. If that is not there, we can do change the RTL. If that is not possible, then we can do the RTL partitioning. We can have multiple, we can add some pipelines, or we can change the RTL code. So at there we can face multiple problems at each stages. So according to your requirement and timing goal, you have to change your methodology, and for meeting the methodology, you should aware of the multiple architecture, you should aware of the multiple SI and P analysis technique, and timing verification and physical verification. So making simulation is not goal. Making simulation and system should be reliable, and we should have first time silicon success. So that should be our goal for making any design, SoC design or ASIC design, or any design, or for making system. First time success is one of the important goal. So if you have any question, you can ask.
Hello, sir.
Yes.
Sir, how can we start writing the .sdc file from scratch for a design?
Constraint file, SDC.
Yes, sir.
Yes, sir. Actually, there are, for any system you require timing constraint. So what are the timing constraint? Basic timing constraint. You should have some timing goal. Like you require clock. Create clock. Okay, this is one of the first step. Then clock will come from some source. Okay. You require one clock. The clock will come from some clock source. That may come from PLL. That may come from some different system. It may come from some function generator. So the clock source will have some characteristics. If it is coming from PLL, so PLL may have some 50 picosecond jitter. Okay. So you have to see from where it is coming. If it is not, you don't know, then you have to study some this clock sources. If it is coming from some PLL data sheet, PLL data sheet आप check कर लो. It will have some figure, jitter figure. Okay. So we have to provide some clock. We have to provide the duty cycle. If it is 50% or 40-60, what is it duty cycle? 40-60. So we have to provide a clock period along with duty cycle, and which comes skew. How we define the skew depending upon your nature of the environment. So PLS is coming with PLS there with 50 picosecond jitter. So we have to take some uncertainty and make that 100 picosecond and 200 picosecond. So PLL2, it will come on board. If it is on board, there are some traces. So if it is coming through LVDS block, or some it is coming from directly PLL chip. So you have to check the PCB traces, length of the traces, and you have to define the clock, the uncertainty of that clock. Okay. Then
so how can we reach the final value of the uncertainty?
Actually, that will that you get from some experience. So when you make system, otherwise you have to goal give if your system is not defined, you are making your own system. Okay, then you have to provide. I have made this uncertainty, so system designer can take away. Suppose you have made one processor, so it is clock is coming through internal PLL or external PLL. External PLL has some 50 picosecond delay jitter. So you can take uncertainty as 100 picosecond or some 200 picosecond. So you have to see the what is the environment. So first thing is clock, then uncertainty, then input delay and driving cell. If it is, if you are getting some through drivers or some in from different system. If that is not there, you can take 1 nanosecond, 2 like we are 100 megahertz. That means that 10 nanosecond period is there. Okay. So for 10 nanosecond, you can take 15 nanosecond or that some 10 times of that clock period. Input delay, output delay. Then in case of load, you have to set load command is there. So you have to write all these constraint in that SDC format. So say load, it is going to suppose some memory processor, it is interfacing with memory chips. Okay. So memory have a pin capacitance of 5 femtofarad, 5 picofarad. The package pin capacitance of that, you have to see the data sheet of memory. Yeah, what is the input pin capacitance? So what are the PCB traces? So you have to add like 5 picofarad. Then it's the your processor will have some IO pads. IO pad will have its own capacitance. Some if you are using IO pad, so IO pad data sheet is there in our PDK kit. So you can 2 picofarad of IO pad, then 5 picofarad capacitance you will of the that next driver, memory or some F244 driver. So you have to get this. You have to read the data sheet and you have to give the this input delay, output delay, clock, uncertainty, and these are the minimum 4 input delay, output delay, clock, and load. These are the minimum 4 constraints are required. Then according to your this environment, you can do false path, multi-cycle path, and other things.
How
But
can we
minimum-
analyze if our circuit has some multi-cycle path or false path?
False path means sometimes there are multiple. You have multiple clock domains. Okay. So some block is working at 100 megahertz. Some block working is at 40 megahertz. Some block is like you have one block processor core is there. You have added some JTAG logic also. JTAG is working on suppose 16 megahertz or 12 megahertz. So there is no relation between your core and the JTAG block. So if there is any path from processor to JTAG that block, so these are the false path. Block A and block, suppose there are certain blocks, block A and block B, which are mutually exclusive. There is no relation between their but it is showing sometime that error. The block A register of block A has termination of register of block B. So we can make that as a false path. Sometimes there are some multiplexer. So the normal block, there are some redundant block are there. So both block are mutually exclusive. Sometimes block A will work and sometimes block B will work. So in that case, we can give false path block A to block B. So designer has to decide. Sometimes multi-cycle path, sometimes that that your instruction may not complete in one cycle. So you have to provide 2 cycle, 3 cycle. But system designer has to decide whether 3 cycle operation is working or not. Some instruction can take 3 cycles. So in that case, I am estimating the output after 3 cycles. So the designer should know whether I require the output in 1 cycle or 3 cycle, 4 cycles, or so according to his requirement.
Is there any way I can know that there is some unintentional false path in the circuit or any multi-cycle path which is unintentionally created during the synthesis or something like that?
No, actually, synthesis will generate all the path. Designer he should know the functionality. Suppose suppose these are the 4 blocks. So if there is if there is connection between like block A and block B, designer should know whether these are connected or not. If it is unrelated, then he can mark as a false path. So designer has to decide whether it is a related path or unrelated path.
Yes.
So
Sir, I have a doubt something regarding pad ring, sir.
Okay.
Sir, how can we include that padding in our design?
You're using which tool?
Sir, Cadence.
No, virtual. You're doing full custom or digital? Innovus or Virtuoso?
Innovus. Innovus.
Innovus.
Yes, sir.
Okay, Innovus. Actually, there you have to make that some CAD frame file is there. Actually, I am using ICC. So similarly, so they are making one file that where do initial floor planning. It will suppose there are 64 pads are there. So after initial floor planning, it will place the pads in some random manner. Okay, where to provide the pitch of the pad and that thing, and yeah, then where to write the floor plan information or IO pad information from that file, from that floor plan, and we can give the position in that text file. So like here, like this pad area and this is shown. Na? So bottom left, like 1, 2, 3, 4, 5, 6, 7, 8, 9 pads are there. So I have to provide this pin position and order. Okay, clock pin is at the center, address 1, address 2, address 3, address 4. Some I have to give that pin position, pitch, and order in that particular floor plan file. And I have to read again that file so that address bus will be placed at the bottom, data bus will be at the right, and all the output will be at the top. And so I have to assign according to my requirement. So I have to first place in random manner, and then I have to write one text file. See, there are like in ICC there are four files, four sides are there, top, bottom, left, right, or east, north, something that kind of there. So I have to specify the pitch between the biopad. I have to change that file. First, you have to do random floor plan and make the changes in that particular file. So there is some option, floor plan, right floor plan, something option is there. You have to go to that normal Innovus documentation.
Okay.
So this floor, there is one text file is there, some IO pad placement or something.
Okay.
Okay, you can get help of cadence which file is. I am not using Innovus, but similar options are there in all this PNR tool. First, you have to do random floor plan and make one that template and edit the template and then read that file, floor plan file, read that template file.
Sir, what happens
Still,
if we what happens if we use the netlist which is generated after the only scene map stage, not scene opt stage in the genus tool? If we use that file for the floor planning and for the further stage, it's okay.
which file?
Let's say if we generate in our genus, we have three commands. So scene generic, then scene map, then scene opt. We have three
Okay.
commands for the
Yes.
for the synthesis purpose. So
Okay.
scene map will map the design with the PDK.
Yes.
Then the scene opt is the command to optimize the design. So I am actually doing the synthesis. So after synthesis, after scene opt, some ports are missing and some things are getting optimized by the tool itself. So
Okay.
some things get missed. So
No,
I
actually,
think
if we, so like there are certain pins or they will get optimized. So for that you have to, there are certain command like don't touch. Like
yes,
it will remove some buffers or it will remove some flip flops. So if you want that after scene map, if if you are getting that cells, you have to say don't touch. That's you have to view U1, U2, U3, that hierarchy, that instance name. Don't touch, so that it will not optimize. It will keep as it is. So set don't touch option is there. You can use that option.
what if we use that netlist file which is generated after scene map for the further DDS generation? It is okay.
And that is okay, no issue.
Okay.
You can, actually when you are doing this thing, you have to analyze what is after that first ELAP and then map, and what is the timing difference between what it has optimized. So you have to do this study, what it is optimized, what with respect to performance, area, and what thing. So the when you are doing this synthesis, you should study what it has optimized. So that
Actually some signals are getting optimized and some ports are getting floated. That's the thing that I'm getting after the scene of command.
so suppose you want to give some that ports and that blocks, you can use that set don't touch. Yes.
Yes. I actually use that thing. So some optimization get reduced, and I'm getting some similar kind of netlist after the boot command.
Okay. So you have to see what You want to give, say don't touch command.
Okay, sir. Thank you. We will now end this session for today. Actually, we have already resetted your session, and thank you
Yes, sir.
for bringing out time for us within your so much busy schedule.
Yes, sir.
And
Sorry for that means I have to you have to stay late back evening. So
no issue, sir. No issue, sir. Okay, thank you for bringing out time for us, actually, sir.
okay, welcome, sir.
And sir, kindly share the PDF file of the PPT so that we can give it to
Okay,
the all the attendees.
okay, I will
Ah,
share the PDF to you. I will share.
okay, sir. Okay, sir. Thank you, sir.
Okay.
Thank you.
Okay,
Thank you, sir.
okay. For any query, you can. This is not limited to this session. If anyone has any query, you can yeah, email or phone. I am
Okay,
always
okay, sir.
open to.
Kindly,
So this is
okay,
not
kindly.
limited to session. So all are welcome. For you can perform and you can manufacture all your SoC or IP at SCL also. So
Okay, sir.
okay, you can take help of Raju sir and other.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Okay. Thank you.